Hi everyone, I'm Lolly, and today I'll be talking about snarks for NP and non-signaling PCPs. This is joint work with my wonderful co-authors, Sam, Yael, Pravesh, Alex, and Surya. First, let's start by recalling the definition of a succinct non-interactive argument, or snarg. In our setting, we have a prover who wishes to convince a verifier of the veracity of some statement. The prover and the verifier also both have access to a common reference string, which is generated by a trusted third party. We will be considering non-adaptive soundness, in which the statement that the prover is trying to certify is fixed before the common reference string is generated. The prover generates a succinct certificate, which it sends to the verifier. The verifier reads the certificate and then decides whether or not to accept or reject the certificate for the statement. We want some properties from a snark system. First of all, we want completeness, which says that the verifier should accept honestly generated proofs of true statements. And we want soundness, which says that no efficient cheating prover can trick the verifier into accepting a false statement. In this work, we construct a snarg which can certify any NP statement under, firstly, the learning with errors, or LWE assumption, and secondly, a mathematical conjecture about multivariate polynomials over the real numbers. I'd like to make some notes here. First of all, we can also replace the learning with errors assumption with any of a choice of standard cryptographic assumptions. But for the purposes of this talk, I'll just focus on LWE. Secondly, I'd like to point out that the second bullet point is not an additional cryptographic hardness assumption. It is a mathematical conjecture that can actually just be proven or disproven mathematically. And I'll talk a little bit more about what we know about the conjecture later in the talk. Okay, so let me give a little bit of a roadmap for what I'll do. First, I'm going to introduce non-signaling PCPs, the other component of the title that I haven't yet talked about. I'll show how they can be used to build a snark using the additional ingredient of homomorphic encryption. I will address barriers that we overcome along the road to constructing a full-fledged snark for NP. And I will state our mathematical conjecture and talk about what we know about it. So first, let's talk about non-signaling PCPs, or NSPCPs, as we'll refer to them for the rest of this talk. In an NSPCP, the prover, as usual, wants to convince the verifier of some statement. The verifier will send the prover some random queries, and the prover will respond with answers to these queries based off of the NSPCP. The verifier will then accept or reject based on the answers that it receives. Completeness and soundness are as expected. Completeness simply states that honestly generated answers should be accepted, while soundness says that if the statement is in fact false, then the verifier should reject with high probability over the random queries. Now, you may be wondering how you can hope for soundness of a system as I've described it so far, because note here that the prover is not actually required to commit to the entire PCP string ever. Usually we think that we get soundness for the PCP because even if the verifier doesn't look at the entire string, the prover still has to construct a good overall string because the verifier is going to check some random points of it. Here, the prover does not have to write down the entire proof string anywhere. However, this is still going to be an object that we can actually construct and hope to get soundness for because of this third condition of non-signaling. So we're also going to require that if the verifier queries two different query sets, Q and Q prime, which are overlapping, then the answers on the intersection, the queries that are in both sets, should be indistinguishable in the two cases. So essentially what we're saying here is that the answers to the queries that are in both query set Q and query set Q prime should not signal which of the query sets was actually queried, like overall, whether it was Q or Q prime, should not be signaled by the answers to the queries that are in both sets. Okay, so now let's see how we can use this object to build a snark. First, we'll start by recalling the snark syntax. We have a statement, we have a common reference string. The prover is going to send over a certificate, and then the verifier will accept or reject. To build a snark from a non-signaling PCP, we'll do the following. And this is work of Yael and friends in 2014. We'll start by defining the common reference string to be encryptions of random queries, Q1 through QL. And note here, we're going to encrypt each query under a different key. So encrypting query Q1 under key K1, Q2 under K2, and so on and so forth. To generate the certificate, the prover will do homomorphic evaluation of the PCP answers to generate the certificate, which consists of encryptions of these PCP answers under all of the different keys that were used for the encryptions in the CRS. So note here that we need a homomorphic encryption scheme that supports whatever kind of operation is needed to generate the PCP answers. So if this only requires linear operations and we just need a linearly homomorphic encryption, for more complicated PCPs, we might need fully homomorphic encryption. But as we talk about in the paper, we show how to use PCPs that do have this property that we only need linearly homomorphic encryption. Then the verifier who holds the secret key for the encryption scheme, I'll talk about this more in a second, will decrypt the certificate to get out the answers to the NSPCP in the clear, and then can just run the NSPCP verifier to decide if they should accept or reject. I'm not going to go into the full soundness analysis, but just to give one bit of intuition, the fact that we're encrypting the queries under different keys means that we're isolating the information about one query away from all of the information about the other queries. And so the prover cannot do weird sorts of correlations when it's generating the answers for the queries. It has to simply answer each query as if it was just one single query. And this is how we're going to enforce that the cheating prover for this SNARG construction is in fact a non-signaling strategy. And then we can rely on soundness of the NSPCP to conclude soundness of this SNARG construction. Okay, so this is the general template for how we'll construct SNARGs from non-signaling PCPs. This template has been used to construct SNARGs for P, SNARGs for batch NP, and more, including NTISP and other classes. However, there is a barrier, or at least one of several barriers along the road to using this template to constructing a SNARG for NP. The first barrier we'll talk about is the non-signaling barrier. So the non-signaling barrier states that a non-signaling PCP for NP must have exponential size. And computing such a PCP makes the prover inefficient, which is a non-starter for SNARG constructions. And so because of this non-signaling barrier, this is why it was believed since the seminal work of KRR that this template would never be successful in building a SNARG for NP. To again just give a little bit of reasoning as to why this barrier, why we believe that that a non-signaling PCP for NP must have exponential size. It's the case that a non-signaling PCP implies the existence of a linear program with variables that roughly correspond to the query sets for the PCP, which decides the language, whatever language the NSPCP is for. This means that if we did have a polynomial-sized non-signaling PCP for NP, that would violate well-believed complexity hypothesis about the hardness of SAT or other representative problems. Okay, so how do you get around this problem? Well, remember, the prover doesn't actually have to compute the whole PCP string, as I talked about when I was defining an NSPCP. So this leads to the first key insight of our work, which is that we can use an exponential size PCP so long as each entry, or really the answers to the PCP queries, are efficiently computable. That's all that the prover needs in order to be efficient. Okay, so we've dodged around this first barrier by using an exponential size PCP with efficiently computable entries. A small digression, I'm going to talk about upgrades to the KRR template since it was first written in 2014. So a line of subsequent works remove the need for the verifier to hold the secret key for the encryption scheme. If you remember, in the template that I described, the verifier needed to decrypt the encrypted answers in order to perform the PCP verification. So this is good because it means that our SNARG is publicly verifiable like we want it to be, but maybe even more importantly, this means that we can now rely on semantic security of the encryption scheme to ensure that the cheating prover's success probability should be the same for any encrypted queries that go into the CRS. In KRR 14, this was only true for random queries being encrypted and put into the CRS, but now we can say, oh, if the cheating spoofer success probability changes when we put a different set of queries into the CRS, then that violates semantic security of the encryption scheme. So now that we've removed the need for the verifier to hold the secret key, this leads to the second key insight of our work, which is that we can use a much weaker NSPCP than previously thought. So as I defined NSPCP soundness, it was that if the statement is false, then the verifier should reject with high probability over the random queries. However, in our work, we show that we can actually rely on this much weaker soundness notion, which simply says that if the statement is false, then there exists a query set where the verifier rejects with noticeable probability. So now to give an outline of our construction, we're using the same template from KRR, using an exponential size NSPCP and the augmentations from subsequent work that remove the need for the verifier to hold the secret key. First, we prove that weak soundness of the NSPCP implies soundness of our SNARG construction. This is under LWE and follows a similar analysis as prior constructions, but also relying on the insights that I mentioned that allow us to use this exponential size PCP and only rely on weak soundness rather than regular soundness of NSPCP. Second, we prove that weak soundness of a particular exponential size NSPCP follows from a mathematical conjecture about multivariate polynomials over the reals. And this theorem uses ideas from linear programming and algebraic geometry. So without further ado, let me now actually state the conjecture and tell you what we know about it. So first, a little bit of background about Hilbert's null-Sallenstots. So this is a foundational result in algebraic geometry. We'll start by considering a collection of polynomials with real coefficients over the hypercube, which we'll call P1 through Pt. The formulation of Hilbert's null-Sallenstots that's helpful for us states the following. If a polynomial f is 0 on the vanishing set of P1 through Pt, which we'll refer to as V, then f is in the ideal generated by P1 through Pt. In other words, there exist polynomials Q1 through Qt, such that f is equal to P1 times Q1 plus P2 times Q2, and so on and so forth. So that's Hilbert's null-Sallenstots. Our conjecture is about how large these Qi polynomials have to be. And our metric for this will be the L1 norm of the coefficient vector of the polynomial. So our conjecture, which we refer to as low norm null-Sallenstots, states the following. So again, we're going to consider a collection of polynomials, P1 through Pt. We will need that these polynomials are Boolean predicates with constant locality, and that the computational problem K-lid restricted to V is NP-hard. So this problem is deciding whether or not a K-lid instance has a solution in V, where, again, V is the vanishing set of the polynomials P1 through Pt. So for this are the conditions that make a set of polynomials P1 through Pt useful for our construction. And the low norm null-Sallenstots hypothesis says that if a polynomial f is 0 on the vanishing set of P1 through Pt, then there exist polynomials Q1 through Qt such that f is equal to P1 Q1 plus P2 Q2, so on and so forth. And that for each of these polynomials, the size of Q1 is polynomially related to the size of f, where again, our size metric is the L1 norm of the coefficient vector of the polynomial. So just to recap, what we prove in our paper is that if this low norm null-Sallenstots hypothesis holds for P1 through Pt that satisfy these properties, then we have a weak soundness of an NSPCP that will allow us to build a SNARG. Okay, so what do we know about the low norm null-Sallenstots hypothesis so far? First of all, it's easy to show the hypothesis if we replace this poly n with a 2 to the n. But this fact only yields an NSPCP with 1 over 2 to the n soundness error, and that's not enough to build a SNARG. Next, I want to note that since the writing of the paper, both some of my co-authors and others have disproven the low norm no null hypothesis for specific choices of P1 through PT, which include the choice corresponding to the Hadamard NSPCP, which we use as the representative example in our write-up. However, whether or not the low norm no null hypothesis holds for another useful P1 through PT, and, in other words, whether or not our approach still produces a sound snark, this remains open. Okay, so zooming out again, I've now told you about our construction. I've told you a little bit about how our soundness analysis proceeds and told you about our mathematical conjecture. So are we done? Well, it turns out there is one more barrier along the road to building a snark for NP that we still have to worry about, and this is the Gentry-Wicks barrier. So the Gentry-Wicks barrier states that there is no snark for NP with a black box security reduction. I'm being a little bit informal here, but I'll still, I think, be able to communicate the main ideas. By a black box security reduction, I mean a reduction which breaks LWE, or whatever falsifiable assumption we choose to base the snark on, by using the cheating prover as a black box, that is, thinking only about its input-output behavior. However, it turns out we've actually already avoided this barrier because our security reduction needs knowledge of the cheating prover's inner workings. Specifically, remember, we're relying on this weak form of soundness, which simply says that if the statement is false, there exists a query set where the verifier rejects with noticeable probability. And in the security analysis, we use this query set without showing how to find it. So, in fact, our security reduction is not black box. Now we've dodged around the second barrier, and so we've really avoided all of the known barriers to constructing a snark for NP. And all that's left is to prove the conjecture, our low norm no null hypothesis, for some useful set of polynomials. And I'll now throw this to the audience and suggest that this be your next problem. Thank you.